Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm Antonio Cremonesi. I'm this one, but the big names are of the people who really, made this work. So it's Darko Zikic and Ben Glocker, the people who are mainly driving these two projects that I will be talking about. And of course, there is a lot of collaboration from many other people, both in here and in other institutions, like at Addenbrooke's Hospital down the road, like Scarlett was mentioning, and also at the University of Washington in Seattle. So we'll be talking about the analysis of medical images. In particular, here we're interested in radiological images. Many of you, have had the misfortune of, breaking their arms or something like that, like I did, and having some, X-ray images of this type taken. This is of, chest X-rays, of course. But in many cases, patients undergo other types of medical scans, such as CT scans of this type, or MR, magnetic resonance scans as well. And there is many other ways of looking inside your body. There is PET, SPECT, there is ultrasound, of course. There is many ways of acquiring medical images. And the amazing thing is that in the past 10, 15 years, the hardware for acquiring these images has improved enormously. The resolution, the quality, the signal-to-noise ratio, the way in which doctors can really, peek inside, the patient's body and trying to figure out what's wrong and what to do about it has improved enormously. On the software side, I have to say that things haven't, been quite as exciting, in the sense that, we have now multi-million pound or dollar worth of machinery to look inside the patient, and then what the doctors do is they look at the pixels and eyeball what's wrong with the patient. So, for instance, in a case of a tumor sort of patient, you look at the patient data, say MR, magnetic resonance, and you say, yeah, that looks like a tumor. It looks like a glioblastoma tumor. It looks like grade 3, but it's all looks like. And then you get a new set of images after a month or a week, and you try to assess whether the tumor is growing or shrinking, whether the radiotherapy or chemotherapy is working or not. And again, the difference may be subtle, but the direction of that difference is really important. Is it shrinking? By how much? Is it growing? By how much? Oh, it looks like 10% improvement. But actually, a lot of other things have changed. You might have eaten a lot more than in other days, and so the shape of this object would have changed a lot. So there is a big problem in the medical image analysis domain, which is that of quantifying the disease, not just assessing what type of disease it is, for which trained doctors tend to be very good at, but also quantifying exactly how big it is. So in the case of solid tumors, there are some very well-established guidelines, international guidelines, which all radiologists are forced to adhere to, and they are complete because they really don't work. So if I have a tumor of this shape, for instance, the RECIST guidelines, they tell me that the only way to measure this tumor is to take the longest segment wholly included within that object and report how long it is. Is it 2 centimeters, 2.5 centimeters, whatever it is. But clearly, this measurement doesn't work when the shape of this tumor is really unusual, away from a spherical sort of shape. Also, the reason why this measurement, and it's not just me saying that this measurement is very wrong, but the doctors themselves say that. Another reason why this measurement is really bad is that it only lives on a 2D plane, but clearly the tumor can grow in 3D in any direction it wants, right? And depending on the type of tumor, you would have very weird shapes. You can also have disconnected regions, called metastases. You have all sorts of weird things happening, and so doctors have got real problems trying to assess and quantify, the progress of the disease, whether a certain drug is having an effect or not. So clearly this is important both for the, in clinical practice for the treatment of a patient, but also in research. So for instance, I'm, I don't know, GlaxoSmithKline or Novartis or whatever other, big pharmaceutical company you know of, and I'm, trying to test a new drug, trying to figure out whether it works or not. Again, there is no good way of doing these sort of things because there is no good way of automatically extracting, quantifying information out of medical images. So we're trying to fix this problem by using machine learning. And why do we use machine learning? Because it's the thing we know works best, when you're dealing with huge amounts of data with, pixel or voxel type of data. Is it clear so far? Any doubts or questions? If at any point you want to raise your arm, please do so. So I'm going to be focusing mostly on two projects. These are only two of the most recent projects we've been working on, but there is a lot more that we do in our small medical team. So in the first project, I'm going to be talking about how we can delineate accurately and in 3D brain tumors of a specific type. And once we have this delineation, we can solve the problem of measuring how big it is, for instance, in terms of its volume, also shape characteristics of this tumor, also other sorts of statistics. We can do it completely automatically. Another thing that we can do completely automatically in Project 2 is look at trauma patients, patients who have been in car accidents or other types of accidents in their workplace. Most of these people, when they get admitted to hospital, they get a CT scan taken. CT scan is particularly good, just like X-rays, is particularly good for visualizing bony structures. So we can visualize the spine and automatically detect the position of the spine and also each individual vertebra and also name them. I will tell you later on why this is important and what kind of results we achieve. So let's start with the first project. So on the left, we have images from the same patient. This is a single patient. We are visualizing the brain of this patient. These images are taken sort of horizontally. Imagine you're halfway through the patient's brain. And each of these images correspond to different acquisition modalities, different ways of visualizing the same data. Effectively, it's the same patient in exactly the same slice position. But one of the very cool things about magnetic resonance is that the parameters of the acquisition modality can be set in very flexible ways, so that you can, for instance, in some case, visualize more of the fluid in the brain. So you can have the blood component show up really bright, or you can have the bony component being visualized very bright, and so on. This last two is what's called DTI, diffusion tensor imaging, which is a very special type of magnetic resonance which allows you to reconstruct the orientation of, say, the white fiber tracks in the brain. So the brain, as you probably know, is made of white matter and gray matter. The gray matter is all very uniform and isotropic, while instead the white matter is the opposite. It's very directional. So there are certain fibers that connect, in a long range, a long distance, certain parts of the brain to certain others. And so DTI is particularly good at visualizing the structure of these white matter tracks. Now, what's interesting is that whatever type of MR channels we have, and however in number they can be 6 or 10 or just 1, it doesn't matter. What we want to do is we want to achieve this. So we want to achieve a semantic, what we call a semantic segmentation. Segmentation means delineation, the same thing. This is visualized in 2D because it's easier, but imagine all of this done in 3D, in the original coordinate system of the patient. And so the color coding, the colors themselves don't mean anything. The fact that they're different is what's important. So in blue, we have the healthy brain. In red, we have the actively proliferating part of the tumor. So that's the most aggressive part. So those are cells which have gone mad, and they're proliferating very quickly, and the tumor is growing. In green, we have the already dead part of the brain, where the tumor has been in previous weeks and has left devastation. There is not much you can do about that. And in yellow, we have the edema. Edema means inflammation. So that's mostly healthy brain, but it's swollen because something is being compressed by the growth of the tumor. There might be some tumoral infiltration in the yellow part as well. So it's very cool if we can get all of this done, and all of this done automatically, because then it means that I can measure straight away without any human intervention how big, say, the active cells region is. And so if from 1 week to the next I see a big difference, then it means that my drugs are working or not working. The fact that I can differentiate between the red, the green, and the yellow parts is extremely important as well, because there was a pharmaceutical company, I actually don't know which one it was, which was trying a new type of chemotherapy for this type of tumor. And the way they were measuring the effectiveness of the drug was by measuring the overall volume of the tumor, so without making any differentiation between the different tissue types. And so after a lot of millions of dollars being thrown at this project, and a lot of trials, a lot of tests, a lot of modifications of the drug, the outcome was this drug is completely ineffective. The reason for that is that the overall volume of the tumor wasn't changing. But actually, when someone had the idea of looking at the individual tissues within that volume, they figured that what the drug was doing was turning red into green, was actually killing the actively proliferating tumoral cells and turning them into necrotic core, which is precisely what the drug was designed to do. So actually, the drug was being extremely effective, but because they were using the wrong measurement, because they didn't have this sort of tool, they couldn't quite figure it out. So that's why these sort of tools are important. So how do we do this? Again, it's very difficult to sit down at a computer and start to write a lot of rules. You can use MATLAB, C, C++, Java, whatever your favorite programming language is. And you say, look, these are different patients. It's clear that the active cells are always bright white. At least in this, it's called T1 gadolinium modality. But actually, there are many cases like around this blob where they're not so bright white. There are many cases where the appearance of the tumor and the necrotic core is very different from other cases, like in this one. Compare this one to this one, for instance. And then you say, oh, wait, there is an exception. Then I put in another if statement. And if the value is between 256 and 100, then do this, otherwise do this. Well, that's the wrong way of doing things. And if you start writing these if statements one after the other, you very quickly get lost. And there are way too many exceptions to way too many rules. So a much better way of doing this is by allowing your computer to learn from experience, from data, what are good features to use. By features I mean what thresholds, what channel am I looking at when reading pixel values? Is it T1 or T2, or do I need to acquire a different scan, like a CT scan, for instance, or not? And have the system learn from all this experience, from all this data that has already been labeled by some experts into tumor, non-tumor, active cells, necrotic core. And once I have learned this model, we call it tumor tissue classification engine, then I can apply this engine to a new previously unseen patient. So now I've got a new image coming for a new patient which the system has never seen before. So I push this into the engine, and some data is spat out that hopefully will correspond to the correct map for these 3 different tissue types. So that's the idea underlying all machine learning research, really. The key is really to design something which works, first of all, and is efficient enough to be able to do experiments with, and also to run in a short enough time in clinical practice. So we, first of all, need to create the label database. So that's the key ingredient for our machine learning-based approach. We need to have a good number of patients, and for all of those, we need to have the ground truth labeling. We need to have an expert, like a doctor, who knows what a tumor looks like and what the different tissue components look like, and can actually come up with this map. So clearly, this is a difficult and very time-consuming thing to do, because for an image like this, you can immediately see roughly where the tumor is. But if I told you what is the active part, what is the necrotic part, and what is the edema, when we try to figure out pixel by pixel which one is which, is very difficult to do. So doing this efficiently, even interactively, even allowing the user to interact with the image and to put in Cs and to provide hints, this is very difficult. Doing it efficiently is very important, not just for this project, but also for what's called radiotherapy planning. So when I have a patient and I figure out that there is a tumor, then what I need to do is I need to plan for the radiotherapy treatment. The radiotherapy is effectively a machine. So the patient lies down on a bed, and then there is a machine with a sort of robotic arm, for instance, which goes around the patient and irradiates the patient with X-rays, for instance. And X-rays we know are dangerous, and it's a good thing that they're dangerous because you can use them to kill the tumor. But of course, they're dangerous also when they go through the healthy tissue. So this radiotherapy planning is meant to maximize the amount of radiation dose that goes into the tumor and minimize the radiation dose that goes into the healthy tissue. So the first step in this planning is for a lot of NHS, the National Health Service employees, to sit down in front of a console like this and actually manually delineate the tumor, but also delineate the healthy organs as well. So it takes between 2 and 8 hours per patient. Okay, so you can imagine how expensive this job is and how tedious this job is as well. So if we can do anything to help, that would be highly appreciated. And we do have something that helps, and this tool, as crummy as it might look, it is already being used at Addenbrooke's, and
Sorry, Antonio, is it error-prone as well? Are there lots of mistakes with the manual segmentation?
Absolutely, absolutely. So because of tiredness and everything else, you tend to make mistakes. Hopefully not too many, but that's just the nature of things. So this interactive tool, interactive, therefore assisted, there is a human in the loop. What you do is, given an image of this type, you provide some hints. Okay, so for instance, you just draw this green brush. Green indicates necrotic core, and then around here, these red brushes, brush strokes, they indicate what I believe is the actively proliferating part of the tumor. And then, after this hint is given, the computer fills in the rest. Okay, so the rest is done completely automatically. So the active rim is completely delineated, and the necrotic core. What's more important is that the interaction happens on 1 or 2 slices only in 2D, because that's the best way we know how to interact with images. But the computation, the propagation of this information happens entirely on 3D. So this is, again, what's called an axial view of the brain, horizontal view. This is what's called a sagittal view, so from the side. You can see the eyes here. Here's the mouth, this is the brain. And this is a frontal view, which is also called coronal. So all this, you see green and red all over. So this computation is all done in 3D. So rather than having to go on every single slice and click on thousands and thousands of points, this can be done by, very, very quickly, just acting on a couple of slices or 3 slices, and it can be done in any orientation. It doesn't need to be only in one orientation. So allegedly, this is a simple example because this is all black inside. So you can say, oh, you know, some of you might be familiar with, you know, region growing or, you know, distance transform sort of techniques. You say, oh, anything will work on this. And you're right, this is a particularly simple example, but it works. You know, this technique works also when applied to more tricky sorts of tumors where the necrotic core, for instance, is very highly variable and highly textured. So that's very good. So we said, you know, this is, you know, a nice, small, self-contained piece of work that has come out of the research we've been doing and has got at least two important applications. One is you use it in its interactive form for radiotherapy planning, but you can also give it to your doctor colleagues to create ground truth data, which then can be used to train the automatic system, the completely automated system. And so we've done so. So, all right, before I go there, so what we've done is, you know, we have we have now about 60 patients from the Cambridgeshire area, all suffering from the same type of tumor. It's called glioblastoma grade 3 or grade 4, where the grade indicates the level of aggressiveness. So that's at the top of the level of aggressiveness. And they are the most aggressive, and they are also the most difficult to detect automatically in images. So we have those. And now what we need to do is we need to train from this training data. We need to optimize our classification tool that will be able to automatically identify tumors in images. For that, we use a...
May I just ask before you switch to the next slide?
Yeah.
So would I imagine that maybe you want something like a cost function that will tell you something like, I want to radiate this area more, but I don't want to radiate this area, and definitely not this area, because it's very probably prone to get mutated or something like that.
Yeah, absolutely.
So this is very discrete, and maybe you want something, or probably you do, I don't know, continuous or more.
You're absolutely right. So doing that is something that another group here in Cambridge is looking at, and this is part of the constrained programming group that we have here at MSRC. So they're looking precisely at that problem. So I've got a certain region, I want to radiate it a lot, certain other, I want to preserve it, save it from the X-rays. Figuring out, and there is a well-defined cost function, which once you minimize, it will give you the exact path for the X-rays, okay? So, and that's all part of the path planning, the radiotherapy planning, I should say, that goes on into modern radiotherapy machines. Now, that's another area of research that we are investigating right now. I'm not the expert there, but there are some people who are, and we're working with the oncologists in Addenbrooke's to really figure this out. Because one problem there with modern machines is that they're very, very sophisticated, but the planning and the optimization takes forever. It takes hours and hours and hours. So before you see the results, you have to wait hours, and then you look at the results and you figure, oh gosh, I forgot to put in another region that I want to preserve because that's in the bone marrow or something. And then you put that in, you send it back to the machine. It's a mess. There is a lot of good stuff that we can do for doctors to improve the quality of healthcare they deliver, really. And also for the doctors themselves to be able to go home at a certain time in the evening, to be honest. So in terms of, once we have the data, we need to choose what machine learning algorithm we're going to use. And there we need to choose between many, right? So machine learning is a very advanced field of research, which is good and bad at the same time, because there are so many algorithms you can choose from. It's difficult to figure out which one is the best for my task. So there is a special class of techniques that we've been studying, which is called decision forests or random forests. And the reason why we're interested in those is because they're particularly efficient. And because they're so efficient, it means that we have some hope of making them work with lots and lots, like millions and millions of pixels or voxel data. And also, what we have recently discovered is that decision forests can tackle many different machine learning tasks. So in machine learning, normally you hear about classification or about regression. So this answers a little bit like your question. So when I want to given some data, I want to figure out whether this data is, I don't know, let's think of images. So is this the image of a beach scene, or is it an image of a street scene, or is it a forest sort of landscape? So that's a very discrete sort of assignment. So that's typical of classification sort of problems. Well, instead in regression, you have continuous predictions. So for instance, given distance from Comberton Village College, which is a very good school in the area, what is the house price? So if I'm looking to move to a different house, I can check against this model to see whether the house I've got my eyes set upon is overpriced or underpriced. So this sort of thing. But the price or temperature is more of a continuous estimate. There are many other things that you can do with the same underlying model, same underlying efficient algorithms. So for instance, classification forests have been used and are used in your living room when you play Kinect games. I'm sure all of you have got Kinect at home. If you don't, you know what to do. So the cool thing is that the underlying technology that makes Kinect work is all based on these sorts of techniques. So you probably have heard of the Kinect depth sensor. It's a camera which manages to read out the color of each pixel, but also the depth of each point, how far this point is from the camera itself. But that's not the end of the question. Now that we have all this information, we need to figure out whether what the camera is looking at is a player trying to play a game, or is a sofa or a television set. You see what I mean? And so the way that is done is by assigning effectively a color coding to each pixel, and each color corresponds to different body parts. So for instance, dark gray, whatever this is, for the left shoulder, blue or light blue for the left wrist and left hand, and so on. This works all based on classification forests. And it's quite fun to see how the underlying technology is the same. What we've been working on for years now is one technology, one machine learning model, which is then applied to either gaming or brain tumor analysis. Very, very diverse applications, but that's what makes this type of research fun. There are other things that we've been using forests for. For instance, I was mentioning earlier, if I have a CT scan, like a full body CT scan, which clearly includes millions of voxels, and even compressed, it might end up being something like 2 GB file, and I know that this is a full body sort of scan, but as a doctor, I'm only interested in looking at the left kidney. This is a side view of the left kidney. So if that 2 GB resides on a remote database, I don't need to transfer the entire 2 GB before I can look at the kidney. If the computer has already detected, say, a bounding box for where the kidney is, then it would be almost instantaneous because it's so much less data. And you can also do this progressively. Then I click on the left kidney, I just get that, and then I get the heart and other things if I'm interested in other regions as well. So this sort of technology is good for software engineering as well. But how does it work? Many of us have probably studied about decision trees. So decision trees are, or tree structures is just a data structure where you have nodes, internal nodes, you have edges connecting the nodes. There are no loops, and that's why it's called a tree and not a graph. And then there are some terminal nodes as well, which I'm showing here as squares, and those are called the leaves. So we can use a structure of this type, for instance, to do very basic, this is a toy example, very basic image understanding. So if I've got a picture of my kids here, I'm trying to figure out whether this is an outdoor scene or an indoor scene, then you can think, oh yes, I know how to do this. If the top half of the image is mostly blue, then it's likely to be an outdoor scene. Okay, so you can write this in terms of a decision tree. So at this node I insert a question, which is the top part blue? It's a test. And so I can follow this branch if the answer is true, and this branch if the answer is false. If I follow this path, then I can have another question, which is is the bottom half of the picture also blue? In which case, maybe I'm looking at a picture of a blue wall, and then it's an indoor scene. And so, if it is false, then I end up, in the right answer, which is, outdoor or indoor. So at the leaf nodes, rather than storing, a point answer, straight indoor, straight outdoor, I can also store probabilities. I can say, 90% probability of it being outdoor, 90% probability of it being indoor, for instance. Which means that, these simple models can be probabilistic. So not only they can give me an answer, is it tumor, is it not tumor, but also have an associated confidence. So if I say, there is a tumor in this patient, but I'm not very confident about my answer, then as a doctor, as a human being, I can look at that piece of information and say, okay, further tests are necessary. Maybe I need to get a different MR scan or something else to make sure that I know the answer. So that's why it's important to deal with probabilities. So I'm not going to present much mathematics, but just to give you a little bit more intuition. So we have some data points, which are represented by these little dots here, which can be represented in a very high dimensional feature space. Could be D, could be even infinite dimensions. So for each, imagine that these points represent pixels, for instance, and I'm trying to classify these pixels as belonging to the active region or the edema region. Then I could extract, color information about, contextual, spatial context, whether it's close to a certain organ or not. All these sorts of information can be all incorporated within one very, very long vector-like representation. And all of this can be used as input to my tree, and the different tests represented here by this H function with some parameters theta can decide whether to send this point to the left or to the right. And these trees can grow to be very, very large. For instance, in the Kinect case, we have trees which are 20 levels deep. So those are quite massive trees, because you have, if it was completely full, you had 2 to the 20 number of tests associated to each node. And being able to make that sort of system run in real time, actually more than real time, is quite an amazing achievement. But the other thing that was discovered recently, actually decision trees are very old news. So we didn't invent them. They were invented 40 or 50 years ago. But recently they've been revived because it was discovered, again, not by us, but by people before us, that if rather than having a single decision tree, you have a collection of decision trees, which are all similar to one another and yet randomly different from one another, the accuracy of your final output becomes a lot better. In particular, you mitigate a big problem in machine learning, which is called overfitting. Overfitting is what happens to, for instance, neural networks, which is once they are presented with training data, they tend to understand and learn that training data extremely well. But then they're not capable of generalizing what they have learned to new, previously unseen data, which we call test data. So the new patient, which has never been seen before by the system, will not be classified, will not be handled correctly by the neural network or by a single decision tree. And we cannot claim that Forest solved that problem completely. It is still the biggest problem in the whole of the machine learning community, but we have seen a lot of evidence that that problem is mitigated hugely. So they are better than anything we know at generalizing. That's the important thing. Okay, I'm not going to go through this. So this is a very toy-like illustration. Imagine that I've got a two-dimensional feature space, and I've got some data points. So each of these points can, for instance, represent companies. For instance, in business terms, we might have X1 is what is their share price, and X2 some other measure of how well a company is doing. And we have this training data, and these 4 sets of clusters of companies. So given a point in any of this white space, we want to classify that point as belonging to one of those 4 classes. So clearly you say, oh, this is very easy. I can just compute the minimum distance to the training points. And that's one way of doing it, except it's not a very general way of doing it because once I've got tons and tons of training points, then it becomes very cumbersome and time-consuming to do so. But also, like I said, we want to be able to track the confidence of my prediction. And what I'm showing at the bottom here is the output of forests trained with some variations. So in this case, this does something that is pretty obvious. Whatever is on the top left quadrant is assigned to the yellow class, whatever is here is assigned to the blue class, and so on. And you might say, that's what I want. But actually, when you look at this other set of results, you see that not only a point here is assigned a blue color, but also the color becomes washed out, which is my way of visualizing a higher uncertainty in the prediction, a lower confidence in the prediction, which makes a lot of sense. So what this shows is that points which either fall in between the classes or are very far away from any training point that has been seen previously gets assigned a certain class, like red or green or yellow, if you really force it to. But the system confidence becomes a lot lower, and that's really what you want. Instead, that doesn't happen here. So this shows a little bit of the sort of flexibility of this type of machine learning models. More examples. But okay, so that's the underlying theory of what happens behind the scenes, both in the Kinect world and in the medical world. But going back to the brain tumor problem, which is our application. Right, forget all this. These are the results that we get. So for each column here, you have a different patient. These are all test patients, which means that they have never been seen before by my computer, by my algorithm. This is the ground truth segmentation. So this is the gold standard. This is what we would like to achieve, what the expert has told us where the different tissue types are for each voxel. And these are the results we get using our forest-based technique. So you see that they're different, but they're not too different. So it's a very, very encouraging results. So despite the fact that the tumor has got very different appearance, location, shape, a lot of variability in the actual size and age of the patient, the system still manages to do a very, very good job, completely automatically. These are some pretty pictures, really, some visualizations just to show that it all works in 3D. And again, we have a good understanding of not only the tumor per se, but also the edema. Another reason why figuring out where the edema is because that gives us a good idea of where the tumor is going to spread next if we do nothing. So it's a great thing to have because right now, this is not used when doing radiotherapy planning, and it should be, because I can adjust the way in which the region in which I focus my X-rays so as to cover a little bit of perhaps healthy tissue, but in the edema region, because just in case I've got a little bit of infiltration of tumoral cells there, I can prevent them from spreading, which would be a fantastic thing to do in these type of tumors. So we get fantastic numbers, whatever. That doesn't matter too much. But project 2, because I don't have too much time, is about a different type of medical images. They look different and they are different, acquired by a different type of scanners. This is a CT scan, which is a little bit like X-ray. So you can see the bones very well. So this is a horizontal view across the abdomen of this patient. So here we've got the spine. Actually, this is close to the thorax as well because I can see a little bit of the ribs. You can see them in 3D here. This is the spine. This is a kidney. This is the liver. So it's actually, you're seeing the patient from the bottom. This thing here is the aorta, a big pipe pumping blood all around, or conveying blood all around. And what we want to do is we want to be able to say, in this view, which vertebra is this one? So you might say, wait, a trained eye would be able to say this straight away. Wrong. Radiologists have got a lot of issues with this they would love to be able to say immediately, straight away, just by looking at this image, what vertebra that is, where it is, T1, T2, T11, T means thoracic, or L1, L2, L3 lumbar, in the lumbar region, and so on. Why is this important? Because when in all radiological reports, if I discover that there is, say, a tumor in this region, then I say is beside the L1 vertebra. The spine, the human spine, is the perfect coordinate system for the human body. It's a reference frame which we are born with, and doctors use all the time to refer their findings to the position in the body. So being able to discover this automatically would be great. Being able to do this automatically is very challenging. Why? Because all vertebrae look nearly identical to one another. So why do we have any hope of being able to do this at all? Well, because in the lower thoracic, early lumbar region, for instance, we know that we are going to be close to kidneys. So if we can discover the context, we know that we are at the bottom of the liver, and we can see a little bit of the kidneys, then we know roughly which region of the spine we're in. And so we need to develop techniques which can make use of context, contextual, spatial reasoning very, very efficiently and very accurately as well. You might say, wait, if I look at the same patient from the side, then I can have a better understanding of which vertebra I'm looking at. Well, even that is tricky, because I need to, what radiologists do is they try to figure out where the lungs stop, and that's the beginning of the lumbar region, and then they count 1, 2, 3, 4, 5. It's very tedious and very time consuming. So being able to solve this problem is very important. Even just to make the problem even more interesting, quite often, in order to reduce as much as possible the amount of X-ray radiation which is thrown at a patient, these images are acquired in a very cropped way, like only just the region that we're interested in is imaged, so that we avoid X-rays all over the place, because it's bad for the patient. And so in this sort of highly cropped views, it's even more difficult to figure out exactly which vertebra is this. So we have said why this is important, and this is the sort of variability we have in our database. So we have both almost full body scans, so we have very highly cropped scans, we have head and neck scans, we have thorax scans or abdominal scans, we have big patients, small patients, all sorts of ages. I want this system to work in all cases. Once again, in the case of a PACS retrieval system, as we were describing earlier, this can also be extremely interesting. If you know this, if the computer knows this ahead of time, you can do a lot of good in terms of a more adaptive, selective retrieval of the images. So what we do is we use a different type of decision forest. In this case, it's called a regression forest. Again, answering your question, we can deal with continuous variables, continuous predictions, rather than discrete ones, in almost exactly the same way. And we have a cost function which is defined in a continuous space, in this case. And then we refine the results using a more generative model, statistical model sort of approach, in the form of a hidden Markov model, although this is already old news and we have replaced this. But, all right, yeah, we get good numbers. These are, the more interesting to look at, visual results. So red is our prediction, and yellow is ground truth. So you can see that, we get very, very close, to the ground truth in all cases. But also, because we have a whole model for the whole spine, we can sort of predict, what happens outside the image as well, which is probably completely useless, but it's still a lot of fun to look at. And these are some videos of our results being done in 3D. So one thing, for instance, that is quite interesting to do is in this video on the left, you see that because now I know the evolution of this curve of the spine, I can actually create a special type of frontal view which is actually evolving with the curvature of the spine. So I can see all the vertebrae in one frontal view, which is something very, very useful to have from a trauma doctor point of view, something which without our technique would be just impossible to do. Yes?
You said you take the context into account to
Yeah.
like assign the names to the vertebrae. So the context is like a detected liver or something, or?
Very good question. We don't know where the liver is, so how can we use the context to inform the position of... Absolutely. So there are many ways in which you can incorporate context. What you have in mind, which is absolutely correct, is what we refer to as semantic context. As in, if I know already what region is the liver or the kidney, then I can use that clearly semantic information, that tagging, to inform the rest. But if we don't know that information, then I can still use what we call, it's just us calling that way, appearance context. So, for instance, in the L1 vertebra, which is about here, if I look, 10 centimeters to the right and 10 centimeters up, I expect to see in that region a certain type of tissue density which corresponds to liver-like densities, right? And then if I look to the left, a certain amount in a certain direction, I expect to see kidney-like tissue densities, right? So I can construct my decision tree automatically, of course, with a lot of these sort of tests where for a given reference point, reference voxel, I can look around a certain distance away in a certain direction at many, many different probe pixels. And if they all look in a certain way, then I cascade through the tree in a certain branch in a certain direction until I get to my destination, to my leaf, and there will be a certain probability that I read out. So that's all we do. Indeed, I did mention context and I didn't explain how we implement it. Very good question. So right now we're working on this even more complex patients where there is huge amount of deformation. This is scoliosis. So this is a frontal view, but the spine is deformed this way, very weirdly. And then this is the same patient after the spine has been straightened up, but a lot of nails effectively have been inserted to make sure that the spine is straight. The algorithm as it stands today cannot quite deal with this sort of patients, not yet, but we're working towards making it work in that case as well. So summary, we can use machine learning to learn how to automatically analyze images. Today here I talked about medical images, which have got a clear impact on clinical applications, on the way doctors do their daily job and the way patients are cured. But what's interesting is that almost exactly the same technology has been developed for Kinect, and so for a completely different type of application, and anything to do with image analysis, really, where the images are of any type, we can think of using these sorts of techniques there. So we're quite excited about this line of research. I think I've answered already a lot of questions, but I'm very happy to answer all other remaining questions you might have.
Okay, questions?
Yeah, thanks very much for the
you.
excellent talk. So this question is about some curiosity.
Yeah.
So I think this technique is really amazing, and can it already be used in some hospital?
Yes.
And then I think, what is the accuracy? I think it's much more important if the patient really have the humor, and you must predict out the humor,
Yeah.
the tumor. Sorry.
So answer to your question, a lot of the technology that I've shown here has been trialed and tested in many hospitals, in particular Addenbrooke's here, which is one of the main research hospitals in Europe, but also the University of Washington in Seattle. So the tumor part has been tested in here in Addenbrooke's, the spine part in Seattle. But also some other work that we didn't quite talk about today is part of a product called Amalga, which is a radiology type of product, which is installed already in many, many hospitals in the United States, and in fact, even in Milton Keynes. Man behind you is responsible for that installation, apparently. And answer to the second question, yes, whenever we have to deal with patients who suffer from very serious conditions, we are correctly so scared of making mistakes. However, things are much better than we think they are, because doctors in the past used to be very, very traditionalist, very conservative, not wanting to accept or use anything that had to do with technology. But the new wave of doctors, they're just like us on Facebook every day, and Twitter and all of that. They're much more happy to use technology, and even if the technology doesn't work perfectly well, they sort of understand how to deal with that. So that's a clear advantage that is coming to bear really in these days. But still, we need to be extremely careful with accuracy and all of that. So what we show with the tumor work has been evaluated and compared to existing state-of-the-art, and we do way, way better in terms of prediction than any existing technique, as far as we can tell. Because there is also the problem of being able to conduct a fair comparison with other techniques. There is a lot of problems in this field. For instance, company or academic research team such and such come up with another technique for doing glioblastoma detection. They publish the results, they don't publish their data set. How can I compare with their algorithm? So it's a very unscientific process right now, which amongst the many things we're doing, we're also trying to change that. We're trying to publish our own data set with the labels so that people can compare against us and have as fair a comparison as possible. You can always say the comparison is unfair, but at least we try to help making it fair. So short answer to your question, good accuracy compared to state-of-the-art. Is it enough for this being deployed for doing real clinical use for glioblastoma patients? We don't know yet. We're working on that with the relevant medical people. There's a question here.
I don't know.
This might be recorded, so that's why you might need it.
So thanks for a very nice talk again.
Thank you.
I have two questions actually.
Mm-hmm.
First one also related to the predictions.
Mm-hmm.
So I think there is also one step about this, and that is prediction in time regarding to the first topic you showed. So you probably have also like time sequences of this data. Is it possible to extend this method also to that? So for example, if I irradiate the tumor somewhere in some way, how it will change?
Yeah. Very, very good question. So in our team, there is someone who is an expert in constructing models of this type of tumor, and temporal models. So he can tell you with great accuracy how the tumor is likely to evolve. For instance, in the case of gliomas and glioblastomas, we know that they prefer to grow in the direction of the white fiber tracts. So they don't grow too much in the gray matter, but they grow a lot in the white matter. And as they grow, they tend to also destroy those tracts, with a lot of implications as well. So if we know where the edema is, we know where the white matter is, which is stuff that now we can know automatically, and we know we have these mathematical models for the evolution of the tumor, then we can put all of these things together, right? And we know we can predict how the tumor is going to evolve, and that can inform our technique. And indeed, right now, in the second phase of this project, we have now temporal sequences for, again, Addenbrook's patients, for which we have, the pre-operative image. We also have the image 48 hours after whatever treatment. It could be either radiotherapy or surgery. The tumor has been removed. And then we have follow-up images as well. So we have a lot more data. And we're trying to look at how to extend this algorithm to work on that whole sequence of data as well.
I see. May I?
Yeah, there was a second one.
So my sort of notion of these machine learning techniques is that you need some sort of critical amount of data, like there is a threshold above which the method just starts to work. So are we quite there yet, or do we just need more collection and
yeah. So answering that question is a lot more difficult because it depends a lot on the data itself, how difficult the problem is inherently, but also depends a lot on what type of machine learning technique you use. Again, this is the problem of generalization, as I was saying. So it's not entirely true that in order for anything to work, you need a huge amount of training data. It's not true. Depends on the problem a lot, depends on how well your algorithm can generalize, even for fewer examples, for a smaller set of training data. So the data we have right now is not even 100 patients. So this is completely a toy example. It's not something that I would ever feel comfortable deploying in the real clinical setting. But this type of work is encouraging our medical partners to acquire more of this data. And so perhaps in 5 years' time, I will be happy to have about 1,000 of these patients. If we have that, I will feel very confident that we will have something that works.
By the way, Jamie will give a Connect talk on
Yes.
Thursday. I'm sure he will touch on that as well and can look at the graph illustrator that was used for the Connect work.
Yeah.
Well, thank you.
Thank you very much.
Final question, perhaps, unless you want to move to coffee. Yeah, another one, yes?
Yes.
Go ahead.
So I'm interested in about error source. So if you cannot exactly predict some of the tumor or not exactly about the vertebrate, and then can you somehow decide where are the error coming from? Is it because of the model or because of parameter or simply because of data or something?
Yes, answering those sort of questions takes most of our time, right? Or is it because of a bug in the implementation? That's the other question, which is very, very likely to occur as well, much more than I would like it to be. Yeah, difficult question to answer, but with these sort of models, you can do a lot of reasoning after the fact. So what's interesting is that with the decision forests, I like them a lot because they are no longer a black box like neural networks used to be. Neural networks, they feel a lot more like a black box. You feed in some data, something happens, and some data comes out. And hopefully that works. But when it doesn't work, then it's very difficult to figure out what doesn't work. With decision trees, you can actually, once the trees have been trained, you can go and inspect every one of the different nodes, both the internal nodes and the leaf nodes, and try to make sense of what features are used where, what has been chosen to be used where, how many times in the trees, and so on. So there have been occurrences where we have done this analysis, and then we figured that, for instance, at the very top part of the tree, some of the features that the system automatically chose to use correspond exactly to other features that in previous papers other authors had manually chosen to use. So that's fantastic to find, because it means that they were right and we are right, possibly, unless we are both wrong. But also the advantage of using the automatic technique is that you have many, many, many more tests to be applied after the few ones that you can choose by hand. So you can do a lot of reasoning after the fact that helps you debug the system and trying to figure out whether there are some bugs or glaring mistakes, or whether you have to design the features in a different way, or whether there is just too much noise in the images to be able to extract any meaningful information. So, okay.
Okay, so thank you very much.
Thank you very
It was
much.
a very interesting talk. Thank you.